Chung-Pei Ma from UC Berkeley to give us a special colloquium today. Before we introduce the title of this talk, I wish to have the honor to briefly introduce our speaker today. Professor Chung-Pei Ma received her bachelor's and PhD degrees, both from MIT, and she was first was assistant professor at UPenn, and starting the year 2002, she joined the faculty of the Department of Astronomy at UC Berkeley, and has been there since. She, well, before telling you more, and you already knew about her various accomplishments in astrophysics, I thought this is very important to share with you. She's actually an avid violinist. This is not just kind of a casual statement, because in the year 1983, while she was still in high school, Beinu, she won the first prize in national violin competition in Taiwan. 全国小提琴比赛冠军. This is just totally unusual. Now then, when she moved on and studied abroad at MIT in Boston, she was actually an exchange student with the famous conservatory, the New England Conservatory of Music in Boston. So while she was studying her physics degree, she got both the bachelor and PhD degrees in physics, studying with her advisors, Bertinger, but also studied with Alan Guth. Now, so this is her career in music. Now, back to physics and astrophysics. She has been her specialty was in various topics such as dark matter and dark energy, cosmic microwave background, galaxy formation and evolution, supermassive black holes, and large-scale structure formation. Especially in terms of she's of course trained and practiced as a theorist, but since I believe 2011 around, but in the past 6 years, she retrained herself into an observationist. She started analyzing data, and this resulted in her various discoveries of supermassive black holes. Notice that in the title, black hole is plural. Now, not of course, not we didn't mean that the whole universe is just one supermassive black hole, but here I just like to let you know that, including the most recent one you saw, her discovery you saw from newspaper, she has actually managed to discover several since 2011, and so this I'd like to report to you. Among her recognition of her scientific accomplishments, she received the Any Jump Canon Award in Astronomy in the year 1997, and the Mary Cooper Meyer Award of APS in 2003. So this is a very impressive record. Now, without further ado, today we are very happy to have Professor Ma telling us about supermassive black holes at the centers of galaxies. Let's warmly welcome her.
Thank you, Professor Chen. Okay, thank you. Yeah, so I would like to give you an update on current status of searches for supermassive black holes at the centers of galaxies. And just as a motivation, I would like to first talk about where astrophysical black holes have been found. And of course, there is this other kind of very interesting type of black holes called primordial black holes. And I believe Professor Chen gave an entire colloquium about that last week. But today I would like to focus on the ones that actually won't evaporate. So in some ways, less intriguing than the primordial black holes. But these are very, very massive, and they are, we are trying to find observational evidences for them and trying to measure their masses. So probably among these two astrophysical types of black holes, I would say that the more mundane, better understood type would be the sort of the stellar mass black holes. And they are the natural end state of a massive star. Stars are like people, they're born one day, they get through the middle age period, and then they die. The very massive stars, much more massive than our own sun, would die as a neutron star or a black hole. And the best evidence for such kind of black holes, one of them is Cygnus X1, and in the binary system, so we can see the main sequence star, but it's transferring mass onto an accretion disk surrounding what we believe is a black hole. And this source is giving out copious X-rays, hence the name Cygnus X1. And because of the binary nature, we have a lot of information. We have a lot more information for us to measure the black hole. So this has been determined to be, about 15 suns, solar masses. Of course, the very exciting recent discovery of the gravity waves by the LIGO team. See how high?
Oh, if you just hold it.
We just hold it?
Yeah.
Okay, I can try that.
If you don't mind.
Do you want to
just
use
holding.
the
I'll try this one.
This is.
I'll try this one. And of course, the most recent, just a few months ago, the discovery of gravity waves by the LIGO team. And this is not just one stellar mass black hole, but there are two of them. And the 36 and 26 solar masses, the 29 solar masses, and believed to have merged to form a remnant of 62. As you can do the simple math, that 3 solar masses of stuff believed to have been radiated as in the form of gravity waves. But these are all both examples of the more mundane type of black holes, and we believe that these objects, although they're not very common because massive stars are pretty rare, but they live everywhere in our own galaxy, and these objects are all the Cygnus X1 is in our own Milky Way, and this binary system is at about 410 megaparsecs away in an external galaxy. But the focus of my talk today would be on the supermassive part, many times the mass of the sun. And these supermassive black holes are believed to be formed mainly at the centers of galaxies. This is where we have been finding them. And the most famous example would be the one at the center of our own galaxy, the Milky Way. And this is an infrared image looking along the disk toward the galactic center of our own galaxy. And the Milky Way black hole is the best studied supermassive black hole because it's closest to us. So people are able to measure individual orbits of stars orbiting the central black hole. Of course, black holes by definition are black, so they don't give out light. So we can't see them directly unless they give out Hawking radiation, but these black holes are too massive to have significant Hawking radiation to be observed. So we need to use luminous tracers. In this case, very impressive adaptive optic observations using the Keck Observatory or the VLT have been able to look towards the galactic center, which is a very crowded, obscured part, but they can pierce through in the infrared, and using the biggest telescopes on Earth with adaptive optics to correct for the disturbances of the atmosphere in order to measure those stellar orbits and to infer what's at the center to give them their Keplerian, mostly, orbits. and the mass is determined quite well to be 4 million solar masses. But that is on the very low, at the very low end of the supermassive black holes. Okay, so I call it a puny one. Okay. And the reason being, by contrast, until 2011, the most massive black hole known is the one at the center of Messier 87, which is a giant elliptical galaxy in the Virgo cluster that's at a distance of 16.7 megaparsecs. And it's a very massive galaxy, a very famous one. At the center, you can see the jet of relativistic particles being accelerated by the central black hole. I don't want to go into details here, but the mass have been measured, in this case, using not individual stellar orbits, because this galaxy is way too far for us to resolve individual stars, but rather using integrated stellar light. We can still get the spectra and to measure their velocity distributions. From that, people are able to infer its central mass as at 6 billion solar masses. And I will come back to this, but the sort of current sort of regime my research team is probing is sort of up to above 10 billion solar masses. And these black holes tended to live in the center of the most massive galaxies. This appears to be the correlation we're finding. Bigger black holes seem to know to somehow live in bigger galaxies, and that's a very intriguing evolutionary sequence we're trying to understand why. But here are just two examples. On the left is a rich, probably the richest nearby meaning 100 megaparsecs, cluster of galaxies, the Coma cluster. This is much richer cluster than the Virgo cluster where 87 lives in, but it's also more distant. And on the left, NGC 4089 is the brightest cluster galaxy, the most massive one in this cluster, and this is where we found 10 to 20 billion solar mass black hole 4 years ago. My former student, Nicholas McConnell, and my research team published this mass. But this system is somewhat complicated, as our error bars were pretty big. And so most recently, and I'll discuss the survey that led to the discovery of NGC 1600 on the right. And that, again, is a very massive galaxy, but as you can see just by in this Palomar Sky Survey photo, that is in a quite isolated region. It doesn't have a lot of friends. It outshines its neighbors by a factor of several, if not more. And in that galaxy, we found 17 billion solar mass black hole. Okay, so these are just two examples of this sort of most massive black holes. And just to move on, there are other places we are inferring the existence of supermassive black holes, especially in the young universe, the very distant universe. And quasars, very, very bright, active galaxies, are believed to be powered by supermassive black holes at its center. But there are no quasars left today. But these seem to be a phenomenon in the young universe, or active galactic nuclei. And also, just like the stellar mass binary system that LIGO found, supermassive black holes can easily come in binaries too. And it's actually quite natural to form a supermassive binary, black hole binary, because galaxies merge. That's how galaxies get to be bigger. Okay, so when two galaxies merge, due to gravity, their individual central black holes naturally come together, sink to the center, dynamical center, and it's very natural for them, energetically favorable for them to form a bound system. So if they can lose even more energy and angular momentum to tighten their orbits, that's a big if, and if they can actually merge eventually, this will be a very exciting source of gravity waves, but not at the LIGO's 10 to 100 hertz range, but in a nanosecond or 100 to 1,000 nanohertz regime, and I'll come back to that at the end of the talk. But here I just want to show you a candidate binary supermassive hole system in this Galaxy NGC 6240, and here on the right you're seeing the Chandra images of two nuclei. They're still fairly far apart, several kiloparsecs apart, so they're not close binary yet, but we believe they're on the, they probably can't stay there for very long. They probably will merge dynamically, but you can see the two X-ray peaks. So why are these black holes, supermassive black holes, important? Well, first of all, they seem to be ubiquitous. Every galaxy that we looked at, we either find one or we find an upper limit that's very, very stringent, very high, which means we don't have actually a galaxy that we can say for sure that it doesn't have a supermassive black hole. Okay. So you hear this a lot, that every galaxy appears to host a massive black hole at its center. And the one reason this is quite important for understanding the universe as a whole is, again, this connection between these supermassive black holes I was talking about in M87 or NGC 4889 or NGC 1600, the nearby elliptical, very dead, boring-looking galaxies, not active at all. They're not quasars. They are mostly just red, dead, galaxies. Comparing them to the high redshift universe of the quasars, we believe that these, obviously the quasars have to evolve to something today. Again, quasars by themselves are very intriguing objects. What's powering them? They're getting an enormous amount of energy. And here is a Sloan Digital Sky Survey compilation of all the known quasars at that point. So each dot is a quasar, and the y-axis is a black hole mass inferred relatively indirectly from their emission line widths. I mean, these objects are way too far for us to study the black hole dynamically like what we're doing with the nearby universe, but you can still using emission line as a proxy to sort of infer, so there are probably a factor of a few uncertainties on in the y-axis, but I think the statistical power of the sample is quite impressive. They may be overall off, but this trend is pretty, I think, pretty robust in that the high redshift is when the universe is young. You can see that a few of these are already in the range of perhaps 1 to 10 billion solar masses, with the factor of a few. But you can see this so-called downsizing of the black hole. As you go to the nearby universe, the black hole masses, the masses of black holes that live in the quasar environment appear to be decreasing. You don't interpret this as a Hawking evaporation of black hole masses. Okay, these are just a population evolution. What this tells us is nearby massive black holes are not living in a quasar environment. Okay, these black holes cannot disappear, they can only grow. So the corollary, the question one will ask is, what happened to these black holes today? Where are their descendants? They're clearly not, their host galaxies are not shining like a quasar anymore because we see very few quasars nearby. So the giant elliptical galaxies that we're targeting are probably the most natural candidates as the dormant descendants of these incredibly active, rapidly accreting objects in high redshift.
What is the big blob at 10 to the 9 and 1.5 redshift? I mean, it seems like a big cluster.
Oh yeah, that's just there's a selection effect in the the quasar abundance. If you plot their number density, they do peak at redshift 2. Okay, so their abundance drop. Their abundance at higher redshift is a little more uncertain, and there is selection effect here due to the Sloan's spectra. So sometimes they redshift out of their range. So the gaps are here are probably not real, but the activity of quasar does appear to peak at redshift 2, and there are various ways to understand that due to galaxy formation. And another very important thing of quasars is for active galactic nuclei, the supermassive black hole activities, they are incredibly important for providing the feedback mechanisms that we need in understanding galaxy formation and to regulate the galaxy's stellar mass growth and their colors and their star formation rate in the massive galaxies. Another way to say this is without the AGN feedback to sort of regulate the gas supplies in the galaxy, we cannot reproduce the observed stellar mass, color, and star formation rate and other properties of massive galaxies. And this is a very, very active area of research. Many hydrodynamical simulations, semi-analytic modeling methods are trying to understand this. So AGN, supermassive black hole activity, really impact the environment they live in on a large scale. Okay, so that's also why supermassive black holes are very important to understand, in addition to just measuring their mass. Okay. So I would like to now talk about observational challenges. I'm talking about the biggest black holes. So usually the bigger the thing is, the easier it is to find. Right? I mean, they have larger gravitational sphere of influence. So why hadn't this been found until the past several years? And there are reasons for that. And people knew very well the reasons. That's why they hadn't been, people were aware of this, so one needed to identify the sort of technology method in order to find them. So one thing is massive, as I said, the more massive the black hole is, it appears that their host galaxy mass is also higher. Okay, but the mass function of galaxies, like the mass function of most things in astrophysics, is a rapidly declining function with mass. So at the high mass end, the number density of galaxies, of massive galaxies, is very low. They're very rare. So in order to find a massive galaxy, which could be the host of a massive black hole, you obviously have to look further. Because you've got to enlarge your search volume. As I said, M87 lives in Virgo. But out of Virgo, which is distance of 16, 17 megaparsecs, M87 is the biggest one. So where would the other massive galaxies be? Well, you got to go to Coma or beyond. Okay? Now, so what's the problem? Well, they're rare, but in order to measure the black hole mass, we need to study the orbits of the stars, the stellar kinematics. We need to measure that to infer the mass using gravity. So one very important number is the sphere of influence, is the region surrounding the black hole within which its gravity wins. Okay, when you go to a very large scale, the mass of the gravity of the black hole is not important. For example, the black hole in the Galactic Center, our Milky Way, our solar system's orbit couldn't care less about what it's doing there, right? Because the enclosed mass is dominated by dark matter and other things. Only when you get very close to the black hole would the gravity win over that of stars and dark matter. So the sphere of influence, however, the further you put it out, the more distant it is. Here it is a sort of rough number. It's basically GM over sigma square, the dispersion of the stars. Okay, so just to give you a rough number, for a million solar mass black hole of a typical velocity dispersion of a host galaxy, the sphere of influence is about 50 parsec. Okay, that's a physical distance. But if you put at 100 megaparsec, which is sort of a typical distance we need to go to find a massive galaxy, it's an angular size of 0.1 arc second. That's a very, very small angular size. Okay, and in a typical great ground-based seeing condition when we go observe in the optical IR, if you get a 0.4 arc second line, you're really, really lucky. Okay, and Hubble Space Telescope, of course, is able to get to a sub 0.1 arc second scale. So you need very high angular resolution in order to study the stars within this this region. And because you got to go very far, this is very difficult to do. So that's one reason. The second reason, however, so one could ask, well, why don't you just use the Hubble Space Telescope? In fact, that's what people did for 10 years, okay, in the 90s. But they were very smart not to target these most massive galaxies, which we're trying to do now. And the reason being that these very, very massive elliptical galaxies, like M87, like NGC 1600, like NGC 4089, if you look at their spatial distribution of stars as a function radius from the center of each galaxy, the so-called, this is a projected surface density, and this is what observers can measure, and this is all obtained from the Hubble Space Telescope imaging. And you can see that and these faint lines are all sort of lower mass elliptical galaxies. They have this, for those of you who are astronomers, you know this is the Volcolor profile or Cersei profiles. They rise toward the center, they're cuspy, okay? And they have a characteristic shapes. But when you go to these very, very massive galaxies, ironically, even though overall their luminosities are higher because they have huge envelopes out there, but at the very central part, within 1 kiloparsecs, their surface brightness flattens dramatically, meaning there's a lag of stars, there's a diffuse distribution of stars. Somehow these stars have all gotten scared away, or they never made their way in. Okay. Basically, there is no light there. And when there is so little light there, it makes the measurements very difficult. Okay, Okay, so we need very high signal to noise in order to get a spectra, in order to get a black hole mass. But there's no light here, so you really need a big telescope, okay, to look at the center of these galaxies and sit on the integrator for hours before you can collect enough photons, basically, to study the spectra. So people were very smart to avoid these targets with HST, which is a small mirror, is 2.7 meters. They were able to study these galaxies, okay? And to study these, we realized, sort of 8 years ago-ish, that you really just can't use HST. You've got to use ground-based 8 to 10 meter class telescopes. But we also need HST type of angular resolution, as I mentioned earlier. So in order to do that, fortunately, adaptive optics or other tricks allow us to have HST type of angular resolution to obtain spectra, high resolution and high signal to noise spectra. Okay, and we also need many other kinds of auxiliary data. We need high resolution photometry in addition to spectroscopy in our orbit modeling work and various other things. Okay, so it takes quite a long time to collect enough data for each galaxy, and we need intensive computer modeling to tease out the black hole. We Monte Carlo the orbits very carefully of the stars in order to get a black hole mass. Okay, but this is the second challenge of finding very massive black holes, the lack of star at the center. But this by itself is also a very interesting question. You can ask yourself, why do these galaxies have a core at the center? Okay, I'll return to that momentarily. So very quickly, the basic idea, it's always easy to explain when one has to do this, especially I was a theorist, so I like this kind of explanation, but when I actually has to deal with data, it's very, very messy. Okay, but the basic idea is that we measure stellar spectra towards the center of galaxies, and these are mostly absorption line systems. There's very little star formation, very few emission lines. But these are all due to various, calcium, magnesium, whatever elements. And these are believed to be, obviously, they're broadened. The absorption line features are broadened from individual stars, right? We're observing integrated number of stars, and so it's the middle part. So stellar templates we all know about, okay? And we're very careful with what stellar templates we choose. We test a lot of that, but I don't want to go into details here. But the idea here is we have stellar templates, we have the observed spectra, and we try to get out what is the distribution of the velocities of the stars that broaden these stars' absorption features, which are very, very sharp into what we observe. Okay, but very importantly, and we're all familiar with Gaussian distributions, so you have a mean, you have a width, sigma, the dispersion. But very importantly here is this distribution doesn't have to be Gaussian at all. In fact, nothing is Gaussian, except for the CMB perhaps, in astrophysics. For the most part, things get messy. So there is long tails, high velocity stars we would like to capture, right? These are very important indications for the black holes when they can move very fast. So we want our spectra to have high enough signal to noise for us to measure the non-Gaussian deviations from Gaussian. So we measure the higher moments, H3, H4, away from Gaussian, in order, and then we feed all that information into our black hole modeling. So I just want to tell you that this is sort of the basic idea. So in terms of a systematic survey, so I talked about NGC 4089, which we found 5 years ago, 4 or 5 years ago. That was sort of an obvious target. Okay, NGC 4089 is the biggest galaxy within 100 megaparsec. It's the most massive galaxy in the most massive cluster, the Coma cluster. Okay, so it's a no-brainer to study that galaxy, and we were able to do that using the Gemini telescope and HST and various other instruments for the photometry part. But after that, we realized that we really need to have a systematic study. Okay, I mean, there are a few very well-known clusters, Virgo, Coma, Perseus, and you kind of run out of them pretty quickly. We just needed to really find who are the most massive galaxies out there and target them systematically. So this is what I initiated in fall of 2013, is why don't we just target simply the 100-ish most massive galaxies, this is by stellar mass, okay, out to distance